Yes, please start.
Okay. Okay. So I thank very much the organizers for inviting me to this great conference in honor of one of creators of modern knot theory. So it is the title of my presentation. So the main object is as follows. Let's consider the space of all smooth functions on the circle or on the line. And if we have a couple of points in the line, then we get a subalgebra of codimension 1 in this space, consisting of all functions taking equal values at these 2 points. Such a pair of points is called a chord by some reasons, and a collection of some of such pairs of points is called a chord diagrams, a chord diagram. So if we have a chord diagram and it's a collection of pairs, so we can consider the intersection of corresponding subalgebras. It is a subalgebra consisting of all functions which have equal values at the endpoints of at the pairs of each at the points of each pair. We say that the chord diagram is independent if the codimension of this subalgebra is equal to D, if all these D conditions are independent. We consider the space of all chord diagrams, of all subalgebras of codimension D defined in this way over all configuration of points running through the line. It is a manifold. It is easy to see that its dimension is equal to 2D. We consider also its closure in the space of all subalgebras of the given codimension. And especially we will consider the canonical normal bundle over it. Any such subalgebra is a linear subspace in the functional space, the subspace of codimension D. And we consider its normal bundle of dimension D. And it will be our main tool. So a trivial remark. So what does it mean that a chord diagram is dependent or independent? In contrast to the usual terminology, I allow some endpoints of chords to coincide. And so we depict each of them. We connect any such point by a segment, by a chord, actually. We consider the union of all this chord. It is some graph. So the collection, this chord diagram is independent if and only if this graph has no cycles. Any cycles gives us some dependence between these conditions. It can be disconnected, but it should have no cycle. It should be a forest. Some chord diagrams, some independent chord diagrams can define the same subalgebra, and it is also easy to see what does it mean. So if one collection of pairs contains the points A, B, and AC, and the other chord diagram contains the pairs A, B, and BC, then of course, and all the rest of the diagrams are the same, then of course they define the same condition and the same subalgebra. And it is easy to see that conversely, they define the same subalgebra if and only if these two chord diagrams can be connected by a finite sequence of such flips replacing the pairs AB and AC by AB and B. So it is a trivial remark. And now, what are the problems? What are the motivations for this one? One problem, most easy problem, but not the original one, is in interpolation theory. Let's consider an n-dimensional subspace in the functional space, in the space of all functions on the line or on the circle, of dimension greater than d. Generically, if we have a subalgebra of our kind defined by an independent d-chord diagram, then generically it intersects our subspace transversally. The intersection of them is n minus d dimensional, so it has the same codimension d in this subspace. But maybe its dimension, the dimension of this intersection, can jump for subalgebras, for some subalgebras. We have a continuous family of such subalgebras. Maybe for some of them, this dimension will jump. Is it avoidable? Is it unavoidable? Can it be avoided by a choice of a very good space, subspace, this n-dimensional subspace in the function space? If n is large enough compared with d, namely it is about twice greater than d, then this problem is empty. We can choose just a set of polynomials of degree n, and then for sure this intersection will have just the dimension, the prescribed codimension n d. It follows directly from the interpolation theorem on the line or on the circle. So the problem is for the values of n between d and 2d minus 1. It is a suspicious area. The other, actually my regional motivation, was from knot theory. Consider the space of all smooth maps of the line or of the circle to R3, which is just the third Cartesian power of the function space. It is a linear space, its topology is trivial, and we have it's the discriminant subset in it. It is a subset consisting of all maps which are not the nodes, the maps which have self-intersections or singular points. This subset is a stratified subvariety. It most important strata, which are most important for the calculation of knot invariance or the cohomology of knot spaces, are the strata swept out by subspaces of codimension 3D, defined exactly by independent d-chord diagrams. We have a d-chord diagram, we have the corresponding subalgebra of codimension d in the function space, and we consider the maps all given by three functions, all of whose three functions belong to this subalgebra. It is a subspace of codimension 3D in the space of all maps. And it is, we get the vector space of codimension 3D over the space of our algebras. Now we can consider essentially the same problem. We consider an n-dimensional subspace in the space of all maps of the line or of the circle to R3. It is some interpolating subspace, interpolating the space well, approximating somehow the knot space. Generically, again, let be again its dimension n be large in comparison with the codimension of our space. It's greater than 3D. Then, in general situation, its intersection with each such subspace is of dimension n minus 3D, of codimension 3D in this space. It is the situation when the intersection is transversal. And again, we have the same problem, whether this dimension can jump for particular subspaces, defined by some Chord diagrams. I can only promise that such jumps are responsible for the troubles in the study of stabilization of cohomology rings of spaces when n grows, this expected source of knot invariance of knot of finite type. So it was my natural motivation for this problem. And now, it are the acting persons. Now let me formulate some results which follow from this study. The first result, the first corollary of this study of my calculations are as follows. Let's denote by I of D the number of ones in the binary representation of D. We take the binary representation of the number D in zeros and ones. Let I of D be the numbers of ones in this representation. Then, if the dimension of approximating space is below 2D minus I of D, then for any n-dimensional subspace of the function space, or the space of functions on the line, there surely exist independent D-Chord diagrams which define subspaces, or actually subalgebras, defining subspaces of dimension greater than n minus d in the in this subspace. It's wrong. Defining the subspace of dimension greater than in this approximating space, here should be phi of n, of phi to the power of n. It means that the intersection of the subalgebra defined by this Chord diagram with this approximating space, this intersection is not transversal, and correspondingly the intersection set has a dimension greater than n minus d. So we have some regularity. Idea of the proof. The opposite statement, the opposite conjecture to this means the following. Well, if all such subalgebras intersect our approximating space transversally, then the canonical normal bundle of our space of all such subalgebras is isomorphic to the d-dimensional subbundle of a trivial n-dimensional bundle. The trivial, actually of trivial n-dimensional bundle with the fiber of which is identically equal to this space. But our calculations, which I will describe later, imply by means of the usual machinery of characteristic classes that the orthogonal bundle of this intersection has non-trivial Stiefel-Whitney class of Stiefel-Whitney classes in dimensions greater than n minus d. This orthogonal bundle according to our conjecture, should be a bundle of dimension exactly n minus d, but it will have non-trivial Stiefel-Whitney classes of degree of or dimension greater than n minus d. Of course, it is a contradiction. So it is a corollary. It is a result. It is a contradiction, and it gives us a proof of this theory. So as corollary, as director of corollary of this theorem, we get the following statement. If d is equal to the, if d is power of 2, then the minimal dimension of the approximating space for which there exists such a function space of dimension e, in which any d independent condition defined as space of dimension d is equal to 2d minus 1. The upper estimate is given by the polynomials, just by polynomials of degree d with 0 free term, and the lower estimate is given by our theorem. The next more technical statement is as follows. Well, it studies, it allows us to prove, not only to prove that the dimension of the intersection set of the intersection plane should jump. Sometimes it allows us to prove also that to estimate the dimension. It allows us to promise you that it can jump not only by 1, but maybe by 2, by 3, in some case, and so on. Well, to formulate, we need some objects. Let's consider this space, very well known for this specialist knot theory, the configuration space of D, of subsets of cardinality D in the plane. It is the classifying space of the braid group in D strings. There is a canonical D-dimensional vector bundle over this space. The fiber of this bundle over a point of this set, it is over a point of this configuration space, it is over a set of cardinality D, is equal to the space of R-valued function on this set. It is just the way to write a number, a real number, at each of the points of this set. It is the canonical object in the configuration, in the theory of configuration spaces. So it is a non-trivial vector bundle because of the action of the symmetric group. And let's consider the Stiefel-Whitney classes of this vector bundle. Actually, everything about the cohomology of this space with the cohomology ring of this space was calculated by Dmitry Fuchs many years ago. And in particular, it calculated the multiplicative structure in this ring and indicated what the exact expressions for the Stiefel-Whitney classes of this canonical bundle. So it is a tentative object, and our second theorem is as follows. Suppose that the dimension of the approximating space n is greater than d, and for some natural number r, such a product, here is a problem, such a product of Stiefel-Whitney classes of the canonical bundle is not equal to 0, and the cohomology ring of the braid group or the group of braids with these strings. Then for any n-dimensional approximating space of the function of the space of functions on the line or on the circle, there exist independent chord diagrams such that the corresponding subspaces are the corresponding subspaces, it is the intersections of corresponding subalgebras with this space are of dimension at least n minus d plus r. So the dimension jumps by r in comparison with the expected dimension of the general situation. Theorem 1, the theorem from the previous page is its special case for r equal to 1. In this case, we take just the first element of it, the product of just one element. And this, if this element is not trivial, then we get the estimate from the previous page. Well, and some ideas how to prove it and what is the braid group doing in this theory. Actually, what is a chord? Chord is a pair of points, pair of points in the line or on the circle. Well, that be in the line, which is just a circle. If we deal with the circle, just forget the one of the points, we get the remaining part is a line. A chord is a point of the plane with coordinates A and B, actually of the half plane, because we can take A lower than B. This half planes is topologically essentially the same as a plane. Its configuration space is topologically equivalent to the configuration space of the plane. The only its difference from what we need from the space of chord diagrams parameterizing our subalgebras consist in the following. Some configurations of this half plane can define dependent chord diagrams and correspondingly dependent subalgebras. They correspond to the chord diagrams having cycles. Then we need to remove this set, let's denote it by delta. We need to remove it from this set, and this removing it perforates it very much and can damage its topology. So nevertheless, it is something very similar to the configuration space of the plane. Consider such a diagram of maps. Here we have our parameterizing space, the configuration space of half plane, the set of chords, of chord diagrams with this discriminant set removed. It has an obvious map to the configuration space of the plane, just an identical embedding. And it has also an obvious map to the space of all algebras, of all coalgebras of the function space of codimension D. Actually, it is also tautological. Any chord diagrams is mapped to the subalgebra defined by this chord diagram. Well, then we have notice that we have canonical d-dimensional vector bands on this space and on this space. Here we have the canonical the standard function vector bundle, And here we have the normal bundle, the fiber of which is a normal space to the corresponding subalgebra. The uneasy, probably it should be called a proposition, but it is quite trivial. It is a trivial observation that these two vector bundles are very similar. And actually, the vector bundles in the middle part of this diagram, which are induced from these two vector bundles by these two maps, are essentially the same. So these two vector bundles, these two vector bundles induce the same vector bundle on the middle space, over the middle space. In particular, the Stiefel-Whitney classes of the induced bundle here, induced from this one, this space under this map, and from this space induced by this map are the same. In particular, so they are the same. And the main technical main technical result, which is indeed complicated theorem, is as follows. The right-hand map, this map, defined by the identical embedding, induce a monomorphic map of cohomology rings from the cohomology of this space to cohomology of this space, or which is the same. It is yes. So it is an embedding. It has no kernel. So it means that if some product of Stiefel-Whitney classes here or any class here is not trivial, then its image in this space is also non-trivial. Then we have the following corollary. If some product of Stiefel-Whitney classes defined over this in this space is not trivial, then the same product, the product of corresponding Stiefel-Whitney classes in this space of the canonical normal bundle in this space also is not trivial, because otherwise it would be induce a zero element here, which coincides with the element induced from here, which is not trivial, which is monomorphic, because it is induced by monomorphic map. So if some product of Stiefel-Whitney class here is not trivial, then it is also not trivial here, and we have plenty of non-trivial cohomology classes and product of Stiefel-Whitney classes of this space of our subalgebras. Our theorems follow almost immediately from this statement and from Fuchs' calculations in the cohomology ring of the braid group. So we observe that some element here is not trivial. Say some Stiefel-Whitney here is not trivial, then the corresponding Stiefel-Whitney here also is not trivial. And as we noticed as on one of the previous pages, here it we get from it the fact that some Stiefel-Whitney class of this vector bundle is not real. It is and so it is an abstraction to the low dimension of the orthogonal vector bundle. So as for theorem 2, we use the same consideration, but not for the single Stiefel-Leitner class, but for some products of them, and we use the Jambeli-Tom-Porteous formula for the cohomology classes, Poincare dual to the sets at which the ranks of morphism of fiber bonds jump somehow, and actually we get the direct proof of our theorem. Of course, I will not draw here all the formulas, but it is written explicitly in the reference. So what are the first examples of these statements? The simplest, the most trivial example is as follows. Let D be equal to 2, we consider two chord diagrams, and N also be equal to N, the approximating space of the function space. Then for any two-dimensional, actually, subspace of the function space, there are independent two-chord diagram satisfied by one-dimensional subspace in this space. Already in this case, there already we have non-triviality of our canonical normal bond. It surely will some of its elements will surely intersect our subspace, two-dimensional subspace, not at a single point. As for theorem 2, the first application of our theorem 2 appears in dimension 6, if we consider 6 chord diagram and approximating space of dimension also 6, then there necessarily will have exist 6 chord diagrams which define the subalgebras which intersect our space, not only non-transversally, but even having the intersection of dimension at least 2, and so on. So we can continue and continue and continue. The last example, which I was able to calculate, is as follows: is D is equal to 80 and N is 80 or 81, then for any n-dimensional subspace, there exist systems of D-independent equality conditions defining sets, defining subsets, of codimension n minus D plus 7, so that the intersection, the set of functions in this approximating space, which satisfy all these chords, all conditions defined by these chords, jumps by at least 7. So it is a series of results of this sort. And now I will speak on some natural generalization, which is in some sense more essential, more correct, but more useful in many senses, except for the one that the calculation in this case are much more complicated. So the spaces of our subalgebras of codimension D defined by chord diagrams, by independent D chord diagrams, have natural compactification just in the space of all that we consider the closure and the space of all subalgebras or subspaces of the given codimension in the function space. Of course, the elements of these closures also are subalgebras, and we get some compact subset and the set of subalgebras. The subalgebras which occur in this way may be very, very exotic. For instance, in the case d equal to 3, when we start from algebras defined by 3 chord diagrams, by diagrams of 3 chords, an algebra which appears as a limit of such algebras can look as follows. It can have a support at 2 points. It will be defined by conditions just at 2 points, A and B of the circle of the line. The conditions are as follows. The first of them is, the subalgebra, this limit subalgebra consists of all functions which satisfy the following conditions. Each function from this subalgebra should have equal values at these 2 points. It is the first condition. Zero derivative at the first point. It is the second condition. And the third condition depends on a point of the projective plane, the point alpha to beta to gamma, and this condition is defined by the following equation. The third derivative at the point A with coefficient alpha plus second derivative at the same point with coefficient beta plus the first derivative at the second point with coefficient gamma should be equal to 0. It is an example, and in fact, we have even more exotic examples of such algebras which occur in this compactification. Nevertheless, all of them can be calculated, and this study is not so difficult for any particular D. But actually, I don't have a common description of all such algebras for all D at the same. Again, the subring of this compactified space is not smaller than the algebra generated by just not smaller than the cohomology ring of the braid group. So all the elements of all the cohomology classes of the braid group define some elements, and even the products of Stiefel-Whitney classes of this space. And they also can define the abstractions in our problem, in our problems. So now, in this case, I will demonstrate the corollaries of this. In the case of the second problem, the second motivating problem, for the knot space. So consider the case D equal to 2, or the case of chord diagrams defined by, or generalized chord diagrams defined by 2 chords. Consider the 6-dimensional normal bundle over CD, which occurs in the knot theory. It is the fiber of it consists of all maps of the circle to the 3-dimensional space, consisting of all maps, given by 3 functions, such that each of these 3 functions takes equal values at the points of each chord. So for each of these functions, it are two conditions, this coincidence. So we get 6 conditions. We get a subspace of codimension 6 in the space of all maps of the circle as a space, and its normal bundle is 6-dimensional. So our previous calculations applied to the knots, the problem of knot theory would imply the following. Our previous calculation in the terms of braid group. They imply, in this case of d equal to 2, only the following, that this fiber bundle is not trivial. It means that if we have a 6-dimensional subspace of the space of maps, approximating space of the space of nodes, then it cannot happen that all our subspaces of codimension 6 intersect it transversally, intersect it at a single point. There surely will be one of these spaces intersecting it as a space of dimension at least 1. It is a corollary of our previous calculation. Using our new consideration of the compactifying space allows to go a bit further. We can prove that not only this normal bundle is not trivial, we can prove even that it is not isomorphic to the subbundle of a trivial 7-dimensional space, or which it may be formulated also as follows. For any 7-dimensional subspace of the space of nodes, there surely exists a two-chord diagram such that the set of maps satisfying these chord diagrams intersects this approximating space at a subspace of dimension at least 2. This extra restriction is, well, it follows from some cohomology class of compactified space, which doesn't appear in the cohomology of braid group. So it is an element of some more rich structure, which gives us more possibilities, more corollaries. But unfortunately, as I already said, the calculations in this in the cohomology of this compactified space are much more complicated than just the calculations in the homology of braid groups, which are granted to us by Dmitry Fuchs. So, it's all, and here are the references. You can just look at it and read it if you are interested by what I said. Thank you very much. I finished.